Like nothing?
Alright, you are unmuted, just so
Just in case Reza makes another comment about why the color of his brain is rainbow. That was so awkward. When I looked up and I saw them laughing, I was like, they hurt me so.
It's a great day. I should just skip class.
You what?
I should just skip class.
Why?
I don't know, it's a great day. This is beautiful. Did you do the 4.6 homework last night, Sammy? Okay.
I'm still catching up because I'm trying to do the earlier homework. I want to do well on this test.
Yeah. You guys coming Friday? Yeah?
Yes.
Trying to get Miss Johnson and Miss Dillon to come too.
That would be so
I have
fun.
not seen Miss Johnson. I should go to her office and say hi.
We should.
She's got class after school.
So many classes after school.
I know.
That's pretty annoying.
It is. It's really annoying that Saturday wants to take so many because it's like I get home at around 2:30 and I basically get home, stay there for 30 minutes and then have to go pick her up. And then by then the sun is setting, so my day's over.
The joy of being the older sister.
No, it's terrible. I'd rather be the younger one. The one that all the family members love. Like all the relatives come and they're like, good to see you, Sammy. So Sally, tell me about what's going on in your life. I'm just like, okay, thanks.
I don't know. I have an after school class, so my sister has to stay late. And she doesn't like it very much.
What class, what after school class do you have?
I have British Lit.
Okay, that's
And
the
then
one.
next semester I have American Lit and Bio Lab.
After school?
1:30 to 4:15.
Ooh. Right now, my chemistry lab is from, my chemistry lab right now is from 2 to 5. But see, those hours wouldn't be that bad for me if I wasn't gonna have to drive 45 minutes to get home after that. Now next semester I'm probably gonna take a hybrid chemistry class that their lab is from 5:30 to 8:30 at night. That's where the struggles come in.
Man, you're not even gonna get home until like 9 o'clock.
And that's on Tuesdays, and then I have to take the humanities for Costa Rica, which I think is gonna be like one for Ireland where it lasts from 6 to 8.
Is yours on Tuesdays?
It's on, I'm pretty sure it's Thursdays. So, I actually really like going late though. And it wasn't the kind of class where it was super difficult. It was just one of those laid back, you get to go.
Yeah, I'm gonna help teach it this semester, and I'm gonna throw in some math in this Irish class.
I should have gone to Ireland this year instead.
In the class, I haven't.
Like, I love going with Miss Johnson, but let's bring some math in now. That's more my forte anyways.
I'm gonna do,
I knew that week.
I had it too, and then I failed this one. We're gonna talk about the Guinness guy that helped with stats. We're gonna talk about the, math behind the Giant's Causeway.
Oh my goodness, that is so cool. That is so cool.
So we'll do the
class
fairy
just
tale
for that.
first, and then we'll do the math behind the fairy tale.
I would take the class just for that.
Man, I just want to sit in the class now. I'm interested.
And I've got to think of a couple other things. Didn't you guys go to, there's like a compass thing somewhere. I can't remember what it's called. It's like a big mound.
Hmm? Was it a grave site? Like a mound?
A grave site where the sun shines in a little
Yeah.
bit? Yeah.
That was the Hill of Tara.
I'm going to do the math behind that too.
There's math behind that too?
Mm-hmm.
Of course, there's math behind everything.
Why couldn't we learn this while I was there?
Do I really want to keep all this?
But see, I don't know if we are actually going to go to the Hill of Tara, but I'll do it anyway.
You know, as much as I loved it, I was so tired at that point because we got from our flight at like 2 in the morning, and she said, okay, time for a full day of activities, time to go to the Hill of Tara. So we're walking around this mushy grass after I've been awake for 14 hours now. I was done. And then I tried to sleep on the bus, but then she gave us like a history lecture on the bus, so I couldn't sleep.
It's like, I'm not in the mood for this.
And then I think Jamie is going to do some music stuff. Jamie McGarrigle.
Do you guys see how many days we have left in this class?
So after this week, we have, what, 2 review days and then 2 final exam days? 2 days. Like, I realize it's not a lot hour-wise, but I wish we could just get it over with in one day.
Get what over with?
The exams. Instead of extend the suffering.
Yeah.
I got to drive
We
this
have
one.
2 more class days and then we have our test.
I made Mom come with me. Just in case.
Well, the good news
Oh my
about having a
goodness, I did
2-day
the math on how much
test
I,
is that you
like,
can
what
go
grade
in
I
and
had to get
study.
for British Lit.
You're like,
have
hey,
an
this
A.
wasn't on
I'm
my
gonna
test.
make an A3 on the final. I have 60 on this paper.
I mean, I'm not
So
going to, but it's just
so-
knowing that I can makes me
I'm not
feel better.
I just
going to.
printed off what I had from
Wait,
last
I
night.
got all the points this time. Last time I got 0.
Oh, right, because you didn't do them all.
Because I didn't do one.
And then history.
That's really sad.
Sorry for an
If you're gonna apologize, at least make a count there.
So-
Sorry for the trying.
Sorry for the random trapezoid.
Because
Is he coming at all?
I think so. He was sick
No,
yesterday.
those are their.
Oh my goodness, he was sick. I mean,
It's probably cold.
but I don't know his germs are on you. Because it's like I'm taking attendance and I'm sitting there.
You're the attendance person. What if you get sick?
But she said to go ahead and take attendance at the beginning of class.
Yeah.
And then if they're late, just mark it as absent and go tell them to Dawkins Castle. But it's like we're seniors and stuff, and we don't really have all the time in the world to just go randomly talk to teachers. So I'm like, I will
And
wait
to find
5
them
minutes.
because half the time they're not in their closet.
Yeah. And like, look at this. He's number 5. Late.
30 minutes late.
Wasn't it?
It was most of the same.
Yeah.
Sammy, my last chem lab is a hydrogen lab.
So
We
is
get to
that.
explode stuff.
Yeah.
Yeah, but we don't
So
know
was ours,
the
but I don't
stuff
think
that
we're going
we're.
It wasn't in the syllabus thing, but I think he's just going to do it. I
To
like
work, he does a lot, and then you guys are fine.
No, it's like we get a nice long worksheet that takes us 4 hours.
Right, so, to say now, before we get started, Questions so far? About that's number 76, I think it was, I said 5. Did that work out? No. So one thing we haven't done is work on any problems using the average value idea. There's several in this section on the average values. Say the average value was, and how do you calculate it? This is the question. Yeah, it's basically just adding up all the values and dividing by the number of values. But if you want the exact average of a continuous function, then you have to add up all of the values, quote unquote, which need to go in the interval. 176, you're supposed to approximate it with 5 rectangles and 10 rectangles. Find exact and then find exact. So an approximation should be easy. Just doing values of 5 values. Can I get a value for n equals 5? Average height? Anybody try the problem? Eddie says she looked at it. Okay. Well, I'll let you say, well, I'll let y'all turn that in tomorrow for grade. Someone going to look at it last time. Great. Now you'll have to do it. And so, one question. Any other questions on this section?
Can we do number 35?
35. Directions say for each functional interval A to B, use definite intervals and fundamental general calculus to find the exact values of A, the signed area, and B, the absolute area of the region of the graph of F, and the x-axis from x to 8, x to 2, 35. 1 over 2x cubed, and 1 to 3. 1 over 2x cubed. Over to the left over. Ideas? Yeah, I guess one thing, I just out of curiosity, I might want to look at what it looks like as a graph. What that looks like as a graph.
Thank you.
We write the functions fx negative 4. Yeah, that's right. Going to 0 like this. Yes. Like it's a straight line. I am on. Yeah, it's kind of like that, but it's skinnier. It's sort of something sort of like that. Looking at one. We want to find the signed area and the absolute area. So, part A, signed area.
That's not what I got either.
how do we find the sine wave? Is this graph accurate? I mean, this is kind of what I was told. Yeah. Roughly speaking.
No.
That's not what I got.
Yeah, that's not what I got either.
I got it looks a lot more like a 1/x function.
So does it cross the axis in here?
No.
Other than at 0, does it cross more than one time?
No.
There's an asymptote at
X equals
x equals 0.
Okay, so then, yeah, it's like it's kind of like x cubed, except it's like, okay, so it's xd goes like this, kind of flattens out in here. Like that, is that what you get?
No, still didn't get that.
Think of that?
No, I put parentheses around the.
Maybe we don't know how to enter functions on our calculator. Did you get? He's an asymptote. Oh, yeah, that looks more like it. Because you can't divide by 0, can you? So there got to be a vertical asymptote at 0. I'm not agreeing with that. What is it now? What is it like this, maybe?
Yeah, that's what I got.
Yeah.
Okay, good. That makes more sense. Because I can't divide by x equals 0. So there's got to be a vertical asymptote. I'm agreeing with that. Okay. So from 1 to 3 in here is what we're looking at. How do we find signed area? That interval from 1 to 3. I'm going to write it as 1/2 x to the negative 3 x. Which is equal to
1/2. Oh, but don't you have to find the derivative now?
You mean antiderivative?
Or the antiderivative?
right here.
Don't you need to find the antiderivative of the equation?
Yes, I need to find the antiderivative of 1/2 x to the negative 3. Evaluate 1 to 3. That's correct. What is the antiderivative of 1/2 x to the negative 3?
That is an interesting question.
It'll be to the negative 2.
Is that right?
What's the power rule for antiderivatives?
Something plus 1.
Yeah.
I think it's just-
Yeah, it is. It's negative 1 here.
So we raise the power by 1, which makes it a negative 2 power. And then we multiply by 1 over that new power. So this is negative 1/4 x. And we can put it as negative 1 over 4x squared, if we like that. 1/3. So that will be, if I plug in a 3, that gives me a negative 1 over 36 minus negative 1 over 4. So 136 plus 9, 36 is 8/30s, negative 1 plus 9 is 8/36 divided by 4 is 2 nights. The calculator's dead?
Yes.
2 nights. Amazing thing, my calculator doesn't need that. Okay, so that's called the assigned area. Now, how do we find the absolute area, or B? Absolute area is integral 1 to 3 of absolute value of 1/2 x. It's going to be the same thing this time because why? Yeah, there's no negative area in here, so the assigned area was already all positive, so the absolute area is equal to the same thing as we had before. On this one. Okay. Find area and area. Absolutely. What other questions? Real quick?
Graphs always above the x-axis. The absolute area is the same thing as the assigned area.
Can we do 51?
Why? Okay. Pick one. Directions say each pair of functions f and g on the interpolate of b use definite intervals on fundamental theorem calculus to find the exact area of the region between absolute values. 51 is 2 over 1 plus x squared and 1. Second. F of x equals 2 over 1 plus x. X. Interval is, what did I say, 0? Now let's try one more time and see if we can. Put 1 plus x squared. That vertical asymptote this time, 2 over 1 plus x squared. Why does f of x not have a vertical asymptote this time? That makes it negative. Now we'll right, Jesus coming in and making his presence. What graph did you get? 2 over 1 plus x squared. Hold up here. We can change my scale. So that's it, but we'll just change my scale. I'll make that a 2 there. Okay. There's that. What's g of x look like? So that's there's g of x. And we are concerned about between 0 and root 3. Let's see, root 3, is that going to be at this intersection point or not? Let's figure out what that intersection point is. How do we figure out that intersection point? We're starting at point 0, root 3, and I need to know where root 3 is. Let's find the intersection. It's that f of x equals g of x. 2 over 1 plus x squared equals 1. I guess that means I have 2 equals 1 plus x squared. So x squared equals 1. So x equals plus minus 1. So apparently that point is at 1, where it intersects right there. But root 3 is a little bit bigger than that. So we're going all the way out to root 3. It's good to know where the intersection point is, because now when I do signed area and absolute area, I'll need that, at least for the absolute area. So, wait, am I finding signed area? Is that what you're saying? Or absolute? Area between. Oh, area between them. Okay. So area between number from 0 to root 3, the absolute value of f of x minus g of x. And we've already discovered that at number 1, so the area between them is different. At 1, between 0 and 1, the area between them is up here. And then after 1, the area is between there. So we'll split this up into the integral from 0 to 1. The absolute value of 2 over 1 plus x squared minus 1, plus the integral from 1 to root 3 of absolute value of 2 over 1 plus x squared minus 1. How do I determine if I can take off the absolute value symbol? How do I get rid of the absolute value symbol, so to speak? So if what's inside the absolute value symbol is positive, then you can just simply remove it. If the inside if the absolute value symbol is negative, you put a negative sign on to make it positive. So on this first one, from 0 to 1, since the x function is greater than the g of x function, then f minus g is positive. So I can just remove the absolute value symbol there. On the second part of the interval, f function is below g function, so the difference is negative, so I need to make it positive by taking the negative of it. Now it's a matter of fundamental theorem of calculus. Got it set up, definite interval. It's now set up and split up to handle the absolute value symbols. Fundamental theorem requires an antiderivative. So what can you come up with for an antiderivative on this? let me rewrite it slightly. Again, we get hung up on these fractions. Like over here, I think the problem on the previous problem, the difficulty was that we had 1 over 2x cubed. But once you see it as 1/2 times x to the negative 3, doing the antiderivative was easy. Well, same thing here. I think we get a little lost on this. What if we, instead of writing it as 2 over 1 plus x squared, what if we write that as 2 times 1 over 1 plus x squared? Now it's easy. It's 2 times.
Oh, it's the tangent thing.
Yeah. So
What is it?
Tangent.
Inverse tangent is correct. So the inverse tangent of x minus, now what about antiderivative of -1 right here?
Minus x.
And then over here it's the same thing, except for the opposite signs because of the fact that we switched orientation of the f and g. -2 inverse tangent of x plus x from 1 to root 3.
Mr. Gaddis,
Yes.
is it possible to subtract the second term instead of looking at the negative equation of it?
Yes, that's the same. Yes, good question. I'm writing it as the negative of the function because I want to make the output of that function become positive. But certainly, by the rules of definite integrals, if you have a constant multiplier in a function, as in a -1, I could pull that -1 in front. And so, yes, so I could have done on this minus the integral like that. It's going to be minus that, which is the same thing. You're absolutely right. By the rules that say a constant multiple can come out of that integral. That make sense?
Yeah, I was just wondering if there was a reason why you were doing it.
I was doing it that way simply because I'm following the rules of what an absolute value definition is. So to subtract it isn't specifically declared by the absolute value. To get to the point of subtracting the integral, you actually have to apply that other rule of a constant multiple. And to me, that's an extra step. So I'm just leaving it as negative function, but whatever. It's all the same. So, or this comes out to be inverse tangent of 1 is pi over 4, so this is pi over 2 minus 1 minus inverse tangent 0 is 0, and that's the 0. Then we have inverse tangent of root 3 is pi over 3 times 2 is what? 2 pi over 3 minus root 3 minus 2 times inverse tangent 1 is pi over 2. Got a pi minus a 2 pi over 3, so it looks like I got a pi over 3. I've got a minus 1 and a minus of a minus of a minus 1, which is another reason I like to go ahead and keep my minus sign in the inside, because now I got 3 minuses I got to keep up with. Minus of a minus of a minus is 3 minuses. A minus 1 there, and another minus 1 is minus 2 plus or root 3. So minus 2 plus root 3. All right. We need to go ahead and cover one last little bit of information here. So we have tomorrow as a review day for our test.
1.7.
That's what we're doing.
Okay.
I'm going to define what's called an accumulation function. Area accumulation function. Area accumulation function is a function of x, so it's a function of x, which is defined as definite interval from the starting endpoint of your interval A up to a variable x that's within x has to be within, so where x is an element of so this is just accumulating the area as you go along the axis of this function f. What might that mean for me? Let's draw a picture what I'm thinking about. Here's my t-axis. This is my f t-axis. Let's try to make a kind of reasonable axis here. I think the more okay, so let's say f t. So here's ft on the interval from 1 to 8. I have a picture there of ft now. So I want to eventually get a picture of from this function. I want to get a picture of the function a of x. So what do you think happens at a of 0. What is A of 0? I can't do A of 0. A of 1. 1's my starting number, I'm sorry. So A of X, what you have to understand is A of X is now defined as, so A of X is defined as the integral from 1 to X of f of t.
No way.
Based on this area accumulation function, here's A of X is defined as integral 1 to X of f of t dt. So I want to plot some points over there, so I'm calculating some points. It would just be 0. How do you decide that was 0? I don't have any width, I can't have any area. So A of 1 is 0. I've accumulated no area yet. I agree. What about A of 2? A of 2 would be all of this area, wouldn't it?
Mm-hmm.
So that might be, I mean, I don't know what my scale is here, but that might be something like at 2, we might be jumped way up to here. Whatever that is. I don't know. Big number. I get an idea of it. What about A of 3? Yeah, I've added more area by A of 3. I've added, if you add up all of from 1 to 3, I've increased my area. It's not going up quite as fast now because I've reached a peak in there, so it's still going up, but maybe not quite as fast as it was before.
It's like a derivative, but
An area.
Then at A of 4, we've added in some more area to the whole process, but again, not nearly as quickly. By the time we get to A of 5, what's happened?
we're going down.
Added a little more area, but we're getting ready to go back down. A of 5 reaches a peak. At A of 6, what have you done when you get to A of 6?
Going
You've
down.
lost some area because you added in some negative area. So A of 6 actually comes back down a little bit. Now with me here? A of 7. Doing some more loss of area. But at A of 7, we've reached another 0 point, and we're going to start adding positive area back on, so it's going to go back up for A of 8.
Got him.
So my function A of X looks like this. Follow that, everyone?
Yeah.
Good. So that's called an area accumulation function. What observations can you make about it?
It's like a derivative, but for integrals.
Yes, it's exactly right. So, for example, what do you observe when this f of x function crosses the x-axis? Then you have a maximum or a minimum local max mints here. So which one's the derivative of which one? I just said it's like a derivative but for integrals, and I agree that there's one of them is a derivative function.
We're gonna say A of X's, right? Or
F of t is the derivative of A of x. Notice again, if this is the derivative function, it's going to tell me when the slopes are 0. At 5, the slope needs to be 0 if this is the derivative, and at 5, the slope is 0. At 7, the slope has 0. So if this is the derivative, it would fit that. But that one wouldn't be the derivative of this.
Yeah.
Because at here, where it's 0 there, this doesn't have a slope of 0 there. So this one is the derivative of that.
Yeah.
It kind of makes sense because how is this one defined? As a definite integral. And we've learned from fundamental theorem of calculus that the definite integral relates to the indefinite integral, which is the antiderivative. So that actually gives us a
Mr. Gaddis,
yes.
is it safe to say that f of t is a prime of x then?
Exactly right. Observationally, a prime of x is equal to f of t.
All right.
In fact, that's called the second fundamental theorem of calculus.
Oh crap.
No. No. Oh, look, it's on the next page.
Actually, a prime of x, we'll call it not f of t, we'll call it f of x. We'll change the variable back to x. So a prime of x is equal to f of x.
How many fundamental theorems are
As,
there?
as an extension, what if a of x is equal to, instead of just simply x, what if it's a function of x, like we'll call it u of x?
X.
So maybe your upper limit is not simply x itself, maybe it's some function of x. What would then be the derivative, do you think? Okay, so what's your favorite derivative rule that you always like to employ?
The sum. Or are you asking for the chine?
Aha, that's right. So how does that work?
Should it be obvious?
It'd be fairly obvious. If this was simply an x, if that was simply an x right there, then you would just put f of x right here. But that's not simply an x, it's a u of x, so we'll put a u of x there. But then when you do the derivative, you also have to do the derivative of the inside, so it's going to be times u prime of
Oh
x.
my gosh. That's pretty meta.
So that's the second fundamental theorem of calculus right there. It's fairly easy to show using the first fundamental theorem of calculus. Okay, well let's show it. Let's prove this one right here, real quick. So if I'm given a of x equals integral from a to u of x of f of t dt, then what? Well, so a prime of x is the derivative with respect to x of the integral from a to u of x f of t dt. Y'all with me?
Yeah.
So I defined an accumulation function, this time having a function of x as its upper bound, and to find the derivative of it, I simply do the derivative. But let's work from inside out. Now the first fundamental theorem of calculus, again, this was continuous. If f is continuous, since it's continuous, then the first fundamental theorem applies. First fundamental theorem, what can we show about this? What can we say about this definite integral? I'm asking you to use the first, or the, let's call it the fundamental theorem of calculus. And this will be called the second. Okay, so using the fundamental theorem of calculus, what can you say about the definite integral shown there? Capital F of u of x minus capital F of a. Y'all agree with that?
Yeah.
Okay. That's the first fundamental theorem calculus. Okay, now how do you do the derivative of that? Got to do a derivative of this and derivative of that. So we're going to have f prime of u of x times, by the chain rule, u prime of x minus, what's the derivative of f of a?
F prime of A. Come on. That's it, right?
Yes. Well, what is f prime of a this time?
A is a constant. It's just
Careful. Remember, a is a constant number, so therefore f of a is a constant number. The limit of any constant number is
0.
That's a 0 there.
Got him.
Almost there. That look like this. Not quite, but can we make it? That's capital F prime is in fact little f by definition of indefinite interval. This was what? Chain rule, constant. We're done. That was easy enough.
Is that the proof?
Yeah.
Great.
Why do we even worry about this accumulation function? It's an interesting thing that is there, and we can talk about it, and we can, it makes sense in many ways. One of the big reasons we have it in the first place is that when we apply the fundamental theorem of calculus, you have to know an antiderivative to do it. You have to know that capital F. Understand what I'm saying? But it turns out there are some functions in the world that don't have a known antiderivative. Classic example is if you were looking at the indefinite interval of e to the x squared, yes. I can't. It's an antiderivative, but I can't write that in any kind of fundamental way. So if that's the case, how do I handle a definite interval from 1 to 3 of e to the x squared dx? Maybe because that's supposed to be the indefinite interval of e to the x squared dx from 1 to 3. But if I can't write this out as a function, as an indefinite interval, as an antiderivative, then I can't plug in 3 and 1 and subtract like we're going to do. So in that situation, we write this as 1 to x of e to the t squared dt. And then we can calculate it using some techniques called related to Euler and Gauss and others, numerical integration. And we can calculate that way. one specific application of this is in statistics. You're familiar with the bell-shaped curve, right? Everyone's heard of that before?
Yeah.
Well, so it turns out the bell-shaped curve has a function, the standard normal distribution.
Dude.
Has a function y equals, let's see, what is it, e to the negative z squared over 2 pi, or the square root of 2 pi. Okay, wait a minute. Square root.
What's that? Then negative 2 to the z?
That's it. E to the negative z squared divided by 2 over the square root of 2 pi.
Oh.
You graph that, if you were to graph that, like make, instead of z, the reason we call it z is because we use c as a standard normal variable in statistics. But if you made an x and graphed it on your calculator, try it real quick. Graph that on your calculator with an x in place of z and see what you get. Don't forget that it's negative of the x squared divided by 2. All that's in the exponent of the e.
Got him.
No, it's negative c squared all divided.
And so you should get a shape something like this. It may be on your scale, unless you zoom in on your scale, it may look fairly flat, but if you zoom in, you'll get a taller peak in there. The point is that in statistics, we use the area under this function to talk about the probability of events happening and to do statistical significance of hypothesis testing. It's all based on the area under this function curve. Well, the area under the function curve, how do you calculate the area under the function curve? Like if you wanted to know the probability of something happening in this region right here from A to B, that would be the area under that function curve would be the probability of something landing in that area, that region. Well, how do you calculate the area? Definite interval. And since the definite interval of e to the negative z squared is, I can't find an antiderivative for it, the only way to handle it is with accumulation of functions. Anyway, so that's accumulation functions and the second fundamental theorem. Real quickly, the book mentions, almost as an aside, but it's kind of interesting, I think, on page 391, an alternate definition of natural log of x. I'm not going to spend a lot of time on it, I just want to mention to you. We learned the natural log of x in pre-calculus as an inverse of e to the x. In pre-calculus, you said that y equals the natural log of x is defined by what? E to the y equals x. Do y'all remember that from pre-calculus definition? So we defined it as an inverse of exponentiation. And now we're saying that natural log of x could be seen as an accumulation function from 1 to x of 1 over t dt. So it's an interesting thing that if you look at a hyperbola 1 over t, which looks like this. We don't care about the negative side, but if you start it at 1, which gives me a 1 right there. If you look at that and look at the area under it, some number x, this area right here from 1 to x is the natural log of x. So that's kind of curious. Of course, it makes sense because the derivative we know about, now we're talking about the second fundamental theorem, then it makes sense the derivative goes back like that as well. Anyways, that's an alternate way of defining the natural log of x rather than simply defining it as inverse of e to the x. We can define it as an integral function. Right, that's it on section 4.7. You should be able to do derivatives of these. I guess let's do one quick example, make sure we're able to do it, and then we'll see what questions we have on anything else. So, quick example.
It's updated. This is not the 1920s. Oh yeah. Oh no. Oh my gosh.
Here's my a of x. A prime of x.
Oh. That's just t squared minus 1.
It's just the derivative of this.
Yeah.
What did we just learn? I just traced it.
That is f of u of x times u prime x.
Yeah, so we just use the function here. It's going to be you're going to go to antiderivative by the definite integral, but then you're going to do the derivative of it, which takes you back to this function, but with this inserted. So inverse tangent of x squared minus 1, but times.
Don't do this to me.
Chain rule. So the derivative of inverse tangent of x is I guess you could even write this as inverse tangent of x squared minus 1 over 1 plus x squared.
Dang.
All that?
Yeah.
That's an accumulation function. Whose upper bound is more than just simply x. And then by the second fundamental theorem of calculus, the derivative of this accumulation function is here. Joey, look back to the question. Well, we're done.
Yeah.
That's one of the problems. You hope there's a bunch of them on the test.
Yeah.
That's easy. Okay. So you need to be able to do that, but that's not hard. You need to be able to talk about accumulation functions, maybe sketch a graph like we did here. Nothing too elaborately hard on this section. Okay, question?
No.
Subway? I have money.
Right. Yeah.
Nice.
The question is what does on this function here, what does a of 4 represent? That'd be a good question. What does
Where's it?
a of 4 represent?
I think it's talking about a specific point on a given a of x function.
Yeah, so the inverse tangent of 4
Oh.
Yes.
That's nice.
of t squared minus 1 dt.
Just trying to metaphysically
so-
understand.
This would be now simply a definite integral
Oh, that's cute.
of this. So you can now you can actually calculate this number if you want it. Versus this is an accumulation function. This is now just a number. But again, as a function, each input has a singular output, and this is the single output at a of 4. So it's just a of 4 is just a regular old definite integral. It's no longer, it's just one point on the accumulation function.
Ooh.
If you calculate that, it would be like what, 1/3 t cubed minus t evaluated from 2 to inverse tangent of 4. So plugging in these numbers here and subtracting would get you the answer.
That's crazy. Dang.
The what is the square root?
That's the derivative
Video after this, or we just
of
studying
this
it?
function.
Not gonna think about
So it's telling me the slope. This is telling me the slope of the tangent lines of this function. So this is a function like over here. Here's a of x. Here's a function. It has tangent lines all around through here, and those tangent lines have a slope to them.
Mm-hmm.
Derivative function gives me the slope of the tangent line. That is my derivative function for this function. Okay. Other questions on this? You need to practice tonight in homework.
Yeah.
Not generally that hard, but you do need practice. Okay. We've got time to do another problem. So, does anybody have any questions on another section or this one?
For right now.
I can't think of my questions I ever asked.
I think you need to practice. We haven't done an average value problem yet, so I think you need to
Yeah.
practice. Let's see you do that for a minute. How about on page 386? Or 387. How about 76B? That we're supposed to find the exact average height. Try that one real quick. Bless you.
Thanks.
I'm so close. Nope. Gone. Is that a banshee on the other side? Yeah, fine.
Nice.
So the question is, where's the C from? I see what you did there. I can't see.
Can't see?
I mean, yeah, that's true as well. Yeah, that's good.
Okay, so
I just hate having decimals on a freaking fraction.
Yeah.
what does this function look like?
I can't see.
Can't see.
I'll tell you what, it's gonna be a exponential function.
What's that?
With the y-intercept at 1. I can at least tell you that
I have a
much.
y-intercept of 1, I agree with that. I think you meant to say, instead of exponential, you meant to say power function. Like that.
Yeah. Yeah, that's what I meant.
Exponential has a variable in the exponent.
Yeah.
So it's something like this.
Yeah, it's pretty wide.
Straight wide.
1. What happens at time 5? Plug in a 5, what do you get? 25 times 10, that's 7.25. So this is 7.25.
Dang, it hasn't grown that much.
Does it look like the average height? I came to about 3.08 if I did my arithmetic right. Does that look like the average height of that function?
Yeah. Wait, so is this a power function or an exponential function? Which did you say it was?
It's a power function.
Okay.
Exponential is the term we use when the variable is in the exponent, the fixed base, and power is the term we use when it's a variable base and fixed exponent.
Okay.
One more question I have, Ben,
Where's the C?
related to this. What is the
C point.
what is the significance of this green line? If I continue the green line all the way across to here,
Was that the area?
area under the green box is equal to the area under
Yeah.
itself.
Yeah.
Defined area.
Can
And-
you?
And there is a special value C
Yeah.
right there, where f of C is equal to the average height. Meaning if I were to form a single Riemann sum rectangle and use my xk star as that C value, this single rectangle would give the exact area under the whole curve. If that was my special x value. That's called the mean value theorem for intervals. Now it's in this same section we're talking about right now. How do you find that C value? .25 t squared 0.252 squared plus 1 equals 3.08. Solve the 2. That's right. Okay. About out of time. Part C, what's the average rate of growth? How's that different from what we just did? This is an average height. Average height is 3.08 feet. What do we mean by average rate of growth? Let's do that real quick. Average rate of growth. Average rate of growth.
Is that a slope?
I heard, yes. When I hear rate, I'm thinking slope, and I'm going to look at the slope between the beginning and end. So the average rate is simply 7.25 minus 1 over 5 minus 0.
That's
the slope of that secant.
Yeah.
So what does that come out to be? 6.25 divided by 5 is
5/4.
5/4, you said?
Yeah.
Okay, so 1.25 feet per year.
Wow.
So that kind of all makes sense. If it's growing on average 1.25 feet per year, and the average height is 3.08, that makes sense. Okay, we'll see you all tomorrow. Practice some. We have a test on Thursday, and tomorrow will be review day for any questions you have on the section covered.
I stayed at the library until 7 yesterday. What do you need to ask?
Just did it. He said 76.
Just do both. Or we could just ask him right now.
Then ask him.
I have a question.
Question for right out of time.
For homework, did you say to do 75 or 76?
I said 76, but then we just did it in class, so I guess it's not. So.
Okay, thank you.
Who did the work on it?
Well, I mean,
You said it's not.
technically all wrote it down.
Yeah, that's right. We all wrote it down. So I guess that homework question is kind of neat at this point, because we just did it. Did I answer your question?
Yep, thank you.
Yeah.
This is our derivative function. I need to come in 5.
Oh, that is.
All right.
Is this, and then, or like 3, that.
I've already.
Yeah.
Yeah, I'm gonna try.
Better to prep now, so you have questions tomorrow.
Yeah,
Wait
because
till
I've worked
tomorrow
on
night.
it. I don't like studying that. Usually,
Exactly. Yeah. Now that's that cramming doesn't do it. Thank you, Jim. Well, the good news is we're not doing it.